All right, we're in unit number 6, page 8 of your notes, and in this particular video we're going to discuss inclined planes, and we're going to connect inclined planes to the amount of work that you do. We've already talked about in a previous unit about inclined planes, so in terms of setting up the inclined plane, I'm not going to spend a lot of time doing that, but I'm going to spend a lot of time connecting that to work. So let's go ahead and read the introduction here and see what they've got for us, and then we'll see if we can go ahead and answer the questions. So example number 4, a 70 kilogram block slides at a uniform motion. All right, so what is uniform motion? Uniform motion we know is going to be constant velocity down a 10-meter inclined plane, inclined 30 degrees with the horizontal, and all that happens in 20 seconds. And we are going to include friction, so we have to include that. So back to the olden days of inclined planes, remember that we have to draw a free body diagram. So we have weight, we have a normal force, we have, let's see, the weight in the x direction, we also have the weight in the y direction, and then since the problem says we have friction, we have to also include friction. So there's our forces, and that's just basically a general free body diagram. Which forces are doing work on the box? Well, we got to remember about work. Remember, work is only done. Let's see, what are the 3 requirements for work? Work occurs when there's a force. Well, we've got basically 3 forces, 1, 2, and 3. Remember, these 2 are the components of the weight. So these 2 comprise this guy. So this is really these 2 guys combined together. So really you want to think about it as 3 forces altogether, not 5. So you got to have a force, you got to have motion, and we have motion, okay, because it is moving down the inclined plane. And the force that you're considering has to be parallel, or a component of that force has to be parallel to the motion. Well, the motion is going to be this way. So we're looking for forces that are either parallel to that or have a component that is parallel to that. So let's just go ahead and knock out an easy one real quick. We know that the normal force is not doing work on it. It's not doing work because it is parallel to the motion, so we don't have to worry about that. So which forces are doing work? Well, friction is parallel to the motion, so we can say friction, and we can say the weight is doing work as well. The weight is doing work because a component of that weight is parallel. Now, I would agree this component is not doing any work, so totally agree there. But we can say work is doing, or the weight is doing work because part of it is parallel to the plane. All right, next one. How much work is done by gravity on the box? Okay, well, we're going to go ahead and run through that and show you how that works. So we have work. We know that work is going to be F dot D. If we want the work done by gravity, then we need to use the force exerted by gravity. Well, we know the force exerted by gravity is really just plain old, it's just the weight. Remember, weight and force of gravity are the same things. So, we're going to do work done by gravity is equal to Fg d cosine theta. So we'll go ahead and unpack that dot product. This guy right here is the weight of the object. So you got to be careful here because we're going to have 2 W's now. This W here is for the work done, but this W here is for the weight. I might just go ahead and write that out so I don't get too confused. Okay, so we know that weight is also equal to mg. So the work done by gravity is equal to mass times g times d times cosine theta. All right, let's see if we can plug that in. The mass from above is 70 kilograms. Acceleration of gravity is 9.8 meters per second squared. You might be, well, do we use the positive 9.8 or do you use negative 9.8? Remember that when you are working with the work equation, this F is a vector, but as soon as you do that dot product, it becomes a scalar. And as soon as it becomes a scalar, you don't need that negative on there. So we're going to use just plain old 9.8. All right, the distance that travels is 10 meters. And then the cosine is going to be the tough part. So let's go back up to the diagram. Well, let me go back here. What is this angle between? It's the angle between these two guys up here, these two vectors, the force of gravity and the displacement. So what is that angle? Well, if I can go use my pencils, like I did in some previous videos, we can say that the force of gravity is down and the motion is parallel to the plane. So we need this angle right here, but it's not 30 degrees. In the problem that they set up, they said this was 30 degrees. So the question is, what is this angle? Well, we know this is 90, and if this is a right triangle and this is 90 and this is 30, well, then this has to be 60 degrees. So it's 60-degree angle between the weight and the motion. We'll use that down below. So I'll go ahead and plug that in. So 60 degrees. All right, plug this in. So 70 times 9.8 times 10 times cosine 60. And then you get a total of 3430, and that'll be joules. And that's how much work was done by gravity. Okay, the next question says how much work is done by the normal force? Well, we already answered that. It's going to be 0 joules, and the reason is because the force of the normal force is perpendicular to the motion. And as soon as it's perpendicular, there's no work being done. So there it is, it's 0. Okay, the next one, what is the net force acting on the object? All right, so the net force acting on the object, well, let's think that through real quick. Net force acting on the object. What is occurring to the object? Isn't the object moving at constant velocity? And if it's moving at a constant velocity, doesn't that mean that the forces are balanced? And if the forces are balanced, then that means the net force must be equal to 0 newtons. So 0 newtons on that one. All right, the next one. What is the net work done in the box? Defend your answer. All right, the net work done in the box. Well, if we use the work equation, and if we want the net work, then we also have to use the net force. Well, the net force, we said earlier in part E, the net force was 0. So if this is 0 newtons times any d times any time cosine theta, and that will give us 0 joules. So the net work done on the box is 0 joules. So we have gravity doing 3,430 joules. The normal force is doing nothing. And the only other thing that is left out there is friction. And that's what we're going to take a look at next. So what is the work done by friction? All right, let's set the equation up for work. So work is equal to F dot D. And if this is the work done by friction, then I need to have the force of friction here. The problem is in the reading, they didn't tell us what that force of friction is. They didn't give us a value for that. And since they didn't give us a value for that, we need to get that value in some other way. Well, the way that we're going to get that value is by using Newton's second law. And we're going to sum up all the forces acting in the x direction. So what are those forces acting in the x direction? Well, we've got the weight in the x direction, and we also have friction in the x direction. Those are the only two forces acting in the x direction. So I'm going to go ahead and insert those. It's negative F of F plus the weight in the x direction. And there is no acceleration. The object is not speeding up, and it's not slowing down. Okay, because part of the problem that they said earlier was that this box is moving at a constant velocity. All right, so let's solve this real quick. We want the force of friction, so the force of friction is equal to Wx. We also know that Wx is going to be mg, and it's either sine or cosine. So if I go back over here, remember this is the angle for that big triangle that we have here, and that's going to be opposite that. And so opposite is always going to be sine. So we're going to go ahead and plug sine into there. So let's sine theta. And the mass that they gave us earlier, well, did they give us mass or not? Let's see what they gave us here. Yeah, they gave us 70 kilograms right there. So we're going to go ahead and say 70 kilograms times 9.8 meters per second squared, and then times sine of, now we got to figure out the angle. So this is the angle, let's see, where did this come from? This is the angle of that inclined plane. So the angle of the inclined plane, or that was this angle in here as well, that's 30 degrees. So let's go back over here. We'll plug in 30 degrees, and then plug everything in. So we get 70 times 9.8 times sine of 30. And we get 343. So 343, and that's a force, so it'll be newtons. Now we needed that, because that's the force of friction. We needed that so we can plug it into this equation over here and get the work done by friction. So here's the work done by friction. The force of friction was 343 newtons times the distance that the box slid. How far did it slide? There it is. It slid 10 meters. So we get 10 meters here. Cosine of. All right, now this theta is going to be the angle between the force and the displacement. So this is friction. So let's see if we can figure out what's going on with that. Friction is right here, so it's pointed up and to the left. Motion is down and to the right. So the angle between them is going to be 180 degrees. So we'll plug 180 into there. Cosine of 180 is -1, by the way, but we'll do it on the calculator. So 343 times 10 times cosine of 180. And that's going to be negative 3,430. So negative 3,430, and that'll be measured in joules. All right, in the next video, I'll finish that off.